Now we are going to discuss about various types of the cavities in the microwave. So like we'll have how wave is going to propagate. Later you see that on the basis of this cavity, we'll have more discussion about this how piston is going to work. So here we'll see mainly about the rectangular cavity as well as we'll see about the quality factor in different conditions, loaded, unloaded. For that, we are going to see. So still you didn't subscribe our channel, please subscribe it and share with your friends. And for the previous already lectures are available in the playlist. So here we have a discussion. What is the cavity resonators? So for this, you should see that if we talk about this waveguide, okay. So there what we have, it is made up of metallic substance. So that resonator is the metallic enclosure in that electromagnetic energy is going to pass, means electromagnetic waves are going to pass. It's going to store the energy also in the cavity. So finally, by the help of storage energy, we can find its equivalent inductance as well as capacitance. So you know about this capacitance and inductance behavior. And when energy is being dissipated, okay, so that with the help of this dissipated energy, we are able to find the equivalent resistance. Okay, so by using storage energy, we'll find the inductance and capacitance, and by the help of dissipated energy, we are able to find the what equivalent resistance. So now we have mainly common cavity resonators what we are using. One is the rectangular cavity, another is the circular, and third one is the ring-trained cavity. So mainly here in this lecture, we are going to focus about rectangular cavity resonators. So what is the resonators? So okay, it has infinite number of resonate modes with different resonant frequency. So frequency for the particular frequency, it had particular modes. So that for the which resonant frequency we are going to get which mode, that will be called as the resonant modes. So it has infinite number of the resonant modes. So when that frequency of that system is going to be equal to the resonance frequency, then we have maximum amplitude of the standing wave. So what is the standing wave? If this is the transmitted wave, and if you are going to obtain the reflected wave in this way, so that is going to form the standing wave. So it will have maximum amplitude when at the resonance frequency. And maximum energy stored in the fields are equal. Okay. So this mode which having lowest frequency, that is called as the dominant modes, that already we have discussion before also. So TE10 is called as the dominant mode. So now in case of rectangular wave cavity, inside this cavity that is going to satisfy the Maxwell equation. So we have different Maxwell equation in differential form as well as integral form. And it is also going to satisfy the boundary conditions. Like we have electrostatic boundary condition, magnetostatic boundary condition. So here also we have tangential components, normal components. Okay. So here what is the situation? That tangential components of the electric field and the normal component of the magnetic field should be vanish. That should not be available. Now here that cavity is shown here. Okay. So this is the part of that rectangular cavity. And here we have this section. And here we are considering that wave is propagating along the which axis? Z axis. So here this length, that dimension is the small a along the x-axis and dimension is a small b along the y-axis, whereas along the z-axis this dimension is given as the small d. Okay, so these are the rectangular waveguide. Now when it is going to satisfy the boundary conditions, so what we have seen that electric field tangential component must be 0 and magnetic field normal component must be 0. So due to this, when we have rectangular cavity means it has 4 walls. So now we have harmonic functions in the z direction that satisfy the condition at other two ends walls. So we have two ends where it should satisfy. Like if we'll talk about this, when we have cuboids, so we have that surface, how many six surfaces are there. So like this here, two ends, front and back ends should satisfy this equation. So this magnetic field Z components, we have HOZ cos m pi x by a cos n pi y by b and sin pi z by d. So earlier we have discussion in the previous chapter, we are talking about only m and n. Here we are considering in all three directions. So here this is the equation for the transverse electric field for the all three component direction, that is m for the x, n for the y and p for the z. So m and p are the number of the half cycles which is available along the x direction, y direction and z direction respectively, and it is the dimension A, B and D respectively along the x, y and z axis. On the basis of that, this expression is written. So this along the x and y we have cos, along the z we have sin. And this value of m is going to be 0, 1, 2, 3, and for n also 0, 1, 2, 3, but p is going to start at 1, 1, 2, 3, 4. Similarly, this electric field components, in case of there we have discussion about transverse electric field. So where we are calculating the Hz. Here we have discussion about the transverse magnetic field, and here we are going to talk about the electric field Z components. So which was cos there, that became sine here, which was sine, that become the cos. So EOZ sine, similar expression sine, now here cos. Okay, everything is same. Where it was cos there, it becomes sine. Only a small change is here. M and N is going to start here from the 1, whereas P is going to start from the 0. Where in case of TE, that we have M and N is going to start by 0 and P was starting by 1. So that a small change is here. So this separation equation for both TE and TM mode is given by K square. That is finally we are trying to find that amplitude part. So M pi A whole square, N pi B whole square, P pi D whole square. So when we'll have discussion about lossless dielectric. So lossless dielectric means that conductivity is going to be 0. So that lossless dielectric we can call as the perfect dielectric also. So in case of resonance frequency, here we can obtain that is 1 by 2 root under mu epsilon, and again overall square root m by a whole square plus n by b whole square plus p by d whole square. So here we have condition of consideration of both transverse electric and transverse magnetic field where resonance is going to take place. When we have this dimension is like this, the dimension along the x-axis is more than dimension along the y-axis, and the dimension along the y-axis is again smaller than the dimension along the z-axis. So dimension along the y-axis of this rectangular waveguide is smaller than the dimension along the x-axis as well as dimension along the z-axis. Then we have dominant mode, that is TE101, M and P. So M is 1, N is 0, P is 1 here. So now here if a straight wire probe is being inserted at the position where we have maximum electric intensity, then it is going to excite a desired mode. Okay. So when we have, at which point we have maximum electric intensity, then a straight wire probe should be inserted, so that particular excited desired mode we can obtain. So that you can see here by the help of diagram. And the loop coupling placed where at the position of maximum magnetic intensity. So this straight probe was placed where at the position of maximum electric intensity. Whereas for the loop coupling, this position of the maximum magnetic intensity is utilized to launch the specific mode. okay, in case of loop coupling, and earlier was the straight wire. So that again, this already we have seen that maximum amplitude of the standing wave is going to occur when at the resonant frequency. So that here you can see that how excitation takes place to obtain the various mode, where we have maximum electric field, where we have maximum magnetic field. That was the discussion about our rectangular cavity. Now we are discussing about the quality factor of a cavity resonators. So by definition, you know that quality factor, and it is also going to measure this frequency selectivity. Okay, this is another parameters. So from the previous lower class, we have quality factor definition. It is 2 pi into maximum energy stored per cycle and energy dissipated per cycle. Okay, so that is the omega W by P, where W is the maximum stored energy and P is the energy power loss. So finally, this formula is important that we need to keep in mind. So at resonance frequency, that electric and magnetic energies are equal. Both energies is going to become equal where at the resonance frequency. So when electrical energy is maximum, then magnetic energy is zero. And when magnetic energy will be maximum, electrical energy will be zero. So both condition is there. Okay. Now the total energy is stored in the resonators. So we have seen on the basis of stored energy, we are able to find the value of the inductance and capacitors. And on the basis of dissipated, we are able to find the resistance. So we are trying to calculate the total energy here. So integral epsilon by 2 modulus of E square dV. And this is the for the electrical, similarly for the magnetic, mu by 2 modulus of h squared dV. This is the volume integral. Okay, that is equal where at resonance frequency. So E and H are the peak values of the field intensity. Now we have calculation for the average power loss in the resonators. So we have waveguides that 4 walls are there where loss takes place. So that is Rs by 2 integral, that is the surface integral, tangential component modulus of magnetic field square into dA. So here Ht is what? Peak value of the tangential magnetic intensity. Rs is the surface resistance of the resonator. Now these two equations, we should substitute that equation 2 and 3 in the equation 1. So then finally what we have there? Omega W by P. So now we have that energy stored W, okay, and now we have energy dissipated per cycle. So both value we have substituted, then we have equation 4 here, and this modulus of H is the peak value square, so that is equal to sum of the modulus of tangential component square plus sum of the modulus of normal component square. So this equation 4 we can be write in the simplified way, that is omega mu volume divided by 2 Rs surface areas. So this is about the volume integral, and this is what we have surface integral, and remaining factors we have as it is. So for any cavity resonator here, that resonance frequency we have 1 by 2 pi root under LC. Since we have energy stored, on the basis of that we have inductor, capacitors. So unloaded quality factors. So when means when the output is not connected with any load, so that is the unloaded quality factors. So that is given as omega naught L by R. So you'll be aware in the other subject like analog electronics also. So now here we have equivalent circuit diagram of the unloaded resonant can be represented with the help of series as well as parallel resonators. Both combination we can see. So here we have generation side, this side we have load here. Okay. So here this is the transformer, this is the binding, N is to 1. Okay. So this can be again have equivalent circuit diagram in this form. So here RLC is same. So this portion is simplified here. Okay. In place of transformer, we are having some factors, N square is being multiplied here. So this is the cavity couple to the generator left side, and here we have equivalent circuits. So we have earlier unloaded quality factors, whereas the loaded quality factors. Here we are going to consider that load parts. So omega naught L by R plus N square ZG. So G is here for the waveguide, impedance of the waveguide. So that condition is that modulus of N square LS should be much smaller than modulus of R plus N square ZG. So now here we have another term is the coupling coefficient of the system. How we are going to couple the systems here. So that is N square ZG by R. Coupling means different components. Our load is being coupled here also. So this equation 9 further, if you substitute the value here, we have in the simplest form, loaded quality factor omega L by R into 1 plus K. So now if you try to write in terms of what was the value for the unloaded quality factors, so that is omega naught L by R. So in place of that, we is written Q naught. Okay, and remaining we have 1 plus K in the denominators. After rearranging this equation 11, further we have, if you try to simplify, we have reciprocal will take 1 by QL plus 1 by Q naught plus 1 by Q external, where Q external is what? Q naught by K, or we can have omega naught L by KR. So this one just we can rearrange, okay, by the help of factorization. And here we have three different types of the coupling coefficients. That is important again here. A separate question they're asking about coupling coefficient also. Otherwise, long question about explained about cavity resonators along with quality factors. So first one is what? Critical coupling. So critical coupling when a resonator is matched to the generators. When resonator is matching with the generators, then K value is 1 here. So then loaded quality factor is going to become 1 by 2 of the external quality factors. So that is 1 by 2 Q naught. In case of overcoupling, so it is like in case of control system, you are reading about under dam, over dam, critical dam, like this also you can correlate. So here overcoupling means K value is greater than 1. So what is happening that cavity terminus at voltage maximum in the input line. So that cavity voltage will be maximum where in the input line at the resonance frequency. So if you are going to consider K equal to rho, then quality factor will become Q naught by 1 plus rho. So in general, we have Q naught by 1 plus K. So here this rho is what here? Standing wave ratio. Now in case of undercoupling means K is less than 1 and K value is going to become 1 by rho, that is 1 by standing wave ratio. Then quality factor is going to become rho by rho plus 1 into Q naught. So rho is what here? Standing wave ratio. So this one finally you can see here in the form of graph. Okay. So in the x-axis we have coupling coefficient that values from 1 to 4, and in the y-axis we have a standing wave ratio that is 1 to 7. So here this is the situation for the undercoupled. Undercoupled means K is less than 1. Overcoupled, this portion from here to here we have, this is the overcoupled, means K is greater than 1. And here you are seeing that K is equal to 1. So this point is the critical coupling. So in the different coupling, we have different values of these loaded quality factors. So that expression is important. So this is one of the important topic of the microwave. Later we'll see again another topic. Please like, share, subscribe, share with your friends so that maximum people can gain the knowledge. Thank you. Thank you very much.